All right, so now we're going to be taking a look at generally um, motion, and we're going to now be exploring some of the physical principles in our course. And we're going to try to relate these to fire behavior wherever possible. And when we look at motion, there really is no concept more fundamental to the effects that motion has on fires than the concept of momentum. So when we talk about momentum in a physical science setting, what we are saying is that that is equal to, we can express this mathematically as being equal to m times v. And m here is going to be the mass of whatever object it is that we're looking at. And then v is the velocity. And you can think of velocity as the speed of something in a particular direction, right? So there is a directionality associated with momentum. So what this means then is if an object is at rest, meaning the velocity is equal to zero, right? Then what that also means by definition, that is that the momentum is also going to be zero as well. So a couple things that we can note about momentum here being expressed mathematically this way, right? We know we can sort of intuitively determine that if the mass goes up, okay, so if this thing increases, then the momentum is going to increase as well. And then we can also determine here, we can deduce that if the velocity increases, v increases, well then the momentum is going to increase as well. Okay, so we say that if you increase one thing and the other thing increases, we say that there's a direct relationship between mass and momentum and between velocity and momentum as well. So this relationship is sort of encompassed in one of Newton's laws of motion. So we're using now, and we're going to get very deep into this, but all of the laws of motion are going to be named after Isaac Newton. Okay, we're not going to talk much about the history of this, but you probably heard of him either in passing or maybe in some of your classes long ago. You talked a lot about Isaac Newton. So his laws of motion are what we're going to be studying here. We're going to try to relate it to fire behavior. So Newton's first law of motion, okay, encompasses momentum. And another way of saying that is that momentum is conserved. So there's several ways you can look at this. Okay, that's one way to approach it, in that a body in motion is going to stay in motion. Another way saying that is that an object's velocity remains constant until the object is perturbed. Okay. Um, a different way to explain or to describe Newton's first law is that an object at rest or in motion tends to stay that way. So we say an object at rest or in motion tends to stay that way unless acted upon by an outside force. So This statement is the same as just saying momentum is conserved. And if you think about some of these outside forces, would be things like these are just a couple examples. Could be friction, could be tailwinds, for example, on a plane. Um, it could be a simple shove of someone or something. So, for example, if I have a road here and I have this block, okay, and I push on this block to start it moving, well, then it's going to start moving in this general direction. It's going to keep moving in that direction unless it's acted by an external force. Well, as you can imagine, as this is moving, there is something slowing it down, and that's going to be friction. That's the outside force here that is acting on it, that is then going to impact both its speed or velocity and then also its momentum. Right? So we have frictional forces that are kind of slowing this down. Okay, so that's uh, Newton's first law in a very general, very simple way. Take a look at some of the units involved. So if I have my momentum being equal to the product of the mass times the velocity, and we use our units, our SI units. Mass is kilograms, velocity or speed is meters per second. So this gives momentum units of kilogram meters per second. We use a little dot there to means multiply by. And that's our unit here of momentum. Remember, this is the same as saying meters per second is the same as meters times second to the minus one. And this multiplied by kilograms would be equal to kilogram times meter times second to the minus one. These mean the same thing. Okay, so just keep that in mind if you see those units. And as a quick reminder as well, we did see the units of newtons before a long time ago. So recall 1 Newton, which is named after Isaac Newton, which is 1 N, is equal to 1 kilogram meter per second squared. Okay, so if I were to do a little bit of math on this, and I take this and if I multiply it by seconds, well then this second here will cancel this. So I end up with 1 kilogram meter per second, okay, which is the same as this unit here. So another way, another unit of momentum that we'll see is 1 Newton times second, right? So this could be the units of momentum as well. So we'll see both of those units being used interchangeably. So Newton seconds, or uh, we have kilograms meter per second. Okay, these are the units for momentum, just using the other units that we've seen previously. Let's take a look at Newton's second law of motion. And what Newton's second law says is that when a force that has a magnitude F acts on an object of mass M, okay, so let's say that I have an object like this. Okay, this is the mass of this object is equal to M, and I provide a force on this F. What happens is that mass, that object, accelerates in this particular direction, which is the direction that the force is actually applied, right? And that's a simple way of describing Newton's second law. Mathematically, we can say force is a product of the mass times the acceleration. Now, where F is force, M is mass, and A is acceleration, as you know, we could, if we wanted to, we could rearrange this equation, and we can say that the acceleration of an object would be equal to the force divided by the mass. So in other words, as the force increases, okay, the acceleration in the direction of that applied force is going to increase as well. And that should make intuitive sense, right? If you increase this force here, we're going to increase the rate at which this object moves. So the acceleration increases. Similarly, what we know from experience is as the mass increases, on the other hand, so if this object gets more massive, but we apply the same force, it obviously is not going to accelerate as fast. So the acceleration then will be less. Acceleration decreases. So what we're seeing is a similar relationship as above. Okay, there's a direct relationship between force and acceleration. And there's an inverse relationship, meaning one goes up, the other one goes down. So that's an inverse relationship between mass and acceleration, right? So uh, again, mathematically, it's not a super complicated equation, but in terms of what it means, it's also very simple. We can do a little bit of mental gymnastics on this to rearrange the equation to solve for any of these variables. So a couple things to note also. So if we know that F is equal to mass times acceleration, well, mass, we know the units could be kilograms, and then acceleration is the rate of change of speed relative to time, and speed is in meters per second. Divided by second would be meters per second squared. So meters per second squared would be the units of acceleration. If we multiply these together, we end up with kilogram times meters per second squared. And guess what? This is the Newton. Okay, so the unit of force is the Newton that we introduced previously. So this is Newton's second law that says when a force of magnitude F is applied to an object of mass m, that object will accelerate in the direction of the applied force. So that brings us to Newton's third law of motion, which simply states that every action is balanced by an equal and opposite reaction. Right, so in other words, for every action, there's a equal and opposite reaction, another way of stating that in terms of something that you are probably used to. If you're using a fire hose, for example, obviously there's a force of water jetting out from the fire hose going in one direction, and that is opposed by the backward force in the firefighters that are actually holding that hose itself. All right, so we experienced Newton's laws all the time in various circumstances, and if you think about a situation where maybe all three of them you see one after the other or simultaneously. If you're in your car, for example, and you accelerate, right? So you tap on the accelerator, the car's going to move forward, but then it's quickly going to start slowing down if you let go of the accelerator. Well, we said that Newton's first law is that that object at rest or in motion will stay that way unless acted upon by an outside force. So when you accelerate the car and it starts moving, it should technically keep moving unless it's acted by an external force. In this case, it's the external force of friction that is slowing down the car itself, right? The the car moves forward in the first place with the first application of gasoline. And if you keep your foot on the accelerator, you're going to go faster and faster and faster. Well, that's Newton's second law, right? Which says that the force of magnitude, or sorry, a force of magnitude F acting on the object will cause it to accelerate in the direction of the force. That's the second law at work when you keep your foot on the accelerator. If you let go of the accelerator and you start slowing down, that's friction. That is Newton's first law. The external force acting there is going to be the force of friction. Now, if you get to an intersection, for example, and realize you're going to run a red light, for example, right, and you hit the brake pedal, well, then your body, right, you go flying forward, your body pushes against the shoulder and seat belts. So that's a force or an action going forward. So your body is going into the seat belts. Well, then the seat belt actually push back on you, right? That's the opposite reaction, and that is an example of the third law in action as well, right? So hopefully that doesn't happen to you, where you have to slam on the brakes, you don't run a red light, but that's a simple case where all three of Newton's laws can be experienced in a very, very simple situation.